So before we can understand set associative caches, let's briefly review the main ideas we have talked about so far. First, we started off with a very simple cache organization where we had the address stored with the data. And then we said, well, that's too expensive because for every 1 byte of data, I need to store the full address. And so therefore the cache overhead was prohibitive. And the way we solved this problem was by increasing the size of the data that is stored per tag. And we called this the cache block. And so now you need to have only 1 tag per cache block as opposed to 1 tag per byte. And that significantly reduced the tag overhead. Now, when you are given an address, we would break this address, we as in the cache would break this address into 2 parts. The one that contains the block offset, which is defined by the log to the base 2 of the number of bytes in the block. So in this case, there are 2 bytes in the block, so therefore we have 1 bit. And then whatever remains in the address would be the tag. So in this case, it's a 4-bit memory that we are assuming, and therefore we have 4 bits. So 4-bit minus 1 is 3 bits. And those 3 bits are physically stored as part of the tag in the cache. Now, if you want to access this cache, you take the address, the cache would divide that into 2 parts, like I said, and then the tag would be compared against all the tags that are stored in the cache. And so if any one of them found a match with the given tag address, then we would declare a cache hit. And it is also important that when the tag matches, the valid bit corresponding to that cache line is set, because we don't want to be accessing an invalid cache line which has been evicted before, or maybe we are just starting off the program, so the valid bit is not set. So the most important thing here to understand is the given tag is compared to all the tags in the tag array. Now the problem with this approach is that the number of comparisons that you need to make is too many. Even though you can do it in parallel, the hardware would require significant number of comparators to accomplish this job. So in order to reduce the cache overhead of performing these many comparisons in parallel, we then talked about an idea called the direct mapped cache. We said, well, the problem is, given an address, I need to go and compare all these tags, and that is too expensive. So how about I reduce the number of possibilities by saying a given cache block can be mapped to exactly 1 cache line in the cache. So the way we accomplished that was by taking the address. We can't really do anything with the block offset, so that's gone. And we grab the remaining least significant bits, as many as we need, to create an index into the cache. So we treated the set of cache lines like we would treat an array in a normal C program. And then we created an index to access that array of cache lines simply by constructing an index out of the least significant bits in the remaining part of the address after leaving out the block offset. So in this example, I have 4 cache lines. So we need 2 bits to index into this array of 4. So then we chose a line index of size 2 bits. Now, the advantage of this cache is, of course, given a cache line index, there is exactly 1 cache line where this particular address can be stored in. And therefore, at runtime, one has to only check the tag that corresponds to that cache line. And therefore, with just 1 comparison, one can declare whether it is a cache hit or a miss. Okay, let's look at the dynamics of how a direct mapped cache would work. So given an address, the cache would break it into 3 parts as opposed to 2 in the case of fully associative cache. We now have this line index. Now the line index would be used to decode, and it's decoded, and then it selects exactly one position in the tag array, and then a given tag would compare to that tag, exactly one comparison, and if it is a hit, then the data corresponding to that cache line would be obtained, and then the block offset would then select the necessary part of that cache block. So if the block offset is 0, you grab the 0th byte. If the block offset is 1, you grab the first byte, and so on. So now let's talk about another extension to this cache architecture, which is called as a set associative caches. Now if you go back to this direct mapped cache design, this is really good in terms of reducing the overhead of comparisons, which in turn helps reduce the cache latency. But the downside is it's too restrictive in terms of where a given cache block can be placed in. So in this case, there is exactly one place in the cache where I can store it. And now the problem is this can lead to poor cache miss rate, because imagine, for example, that the program happens to access just 2 cache blocks, the ones that I am marking on the slide here. Unfortunately, they both happen to map to the same cache line. And so they would repeatedly thrash each other and evict each other out of the cache. And so you have a pattern, let's say like AB, 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 where A refers to this cache block over here and B refers to this cache block over here. Now you would end up with a cache hit rate of 0, and that's not really good in terms of cache performance, because you really have extra cache capacity. So it's certainly not because you didn't have cache capacity that you ended up with the 0% cache hit rate. It's really because of the cache organization, where we ended up mapping 2 cache lines that are frequently accessed to the same place in the cache. So is there a middle ground where we avoid the overhead of tag comparisons in the case of fully associative cache, but at the same time we enjoy a little bit more freedom than